Hi, welcome to our presentation. This is Dr. Kanimoli, Associate Professor from Vailtuk University. The topic of our presentation is Design of all optical Chalcogenide T-flip-flop using Photonic Crystal Waveguide. The outline of our presentation to be followed by motivation, then realization of T-flip-flop using Photonic Crystal Waveguide, next band gap diagram followed by numerical simulation, then conclusion. Quite recently, the domain of optical devices remains as a central fascinating research field tending to replace digital computing techniques owing to its matchless merits such as ultra-high speed, greater switching action, and wide bandwidth. Therefore, all optical devices were found applicable in high-speed optical networking and computing. Also, it works as a memory element for the optical devices. In conventional waveguide, such as fiber optic cables, light is confined by total internal reflection. One of the weaknesses of such waveguide is that creating bends is difficult. Unless the radius of bend is large compared to the wavelength, much of the light will be lost. This is a serious problem in creating integrated optical circuits since the space required for large radius bends is unavailable. Whereas in case of photonic crystal waveguides, it operates on a different principle. A linear defect is created in the crystal which supports a mode that is in the band gap. This mode is forbidden from propagating in the bulk crystal because of the band gap. That is, waveguide operate in a manner similar to resonant cavities. The attracted feature of photonic crystal waveguide is compact in size and having strong confinement of light and less power dissipation. The reason for choosing chalcogenide material for the realization of T flip-flop is that it offers large ultra-fast third-order nonlinearities, low two-photon absorption and the absence of free carrier absorption in a photosensitivity medium, and having a transparency from near to the far infrared spectra and photosensitivity to the bandgap light is another important property that chalcogenide glasses exhibit. The T flip-flop is realized by concatenating the XR gate with D flip-flop. The input to this design or TCL is nothing but the previous state of D flip-flop and the third input is clock and the output ports are QN and QN dash. And the T flip-flop is a design with an array of 26 cross 13 chalcogenide rods exposed to air substrate arranged in square lattice maintaining lattice constant of 600 nanometer, and the radius of these rods is optimized to have 0.19 A. The band diagram shows possible photonic bands of transverse electric and transverse magnetic modes. This is a dispersion relation for the guided mode created in a two-dimensional photonic crystal by removing a row of rods. The photonic band gap has a wavelength range between 1029 nanometer and 1955 nanometer, and this is the electrical field distribution in a waveguide exhibiting transmission. In the first diagram, when t equal to 0, that is when the t input is not energized by light rays, whatever the light signal present at CL input going to appear at the next stage of QN. Whereas in the next diagram, when the T input is energized by light rays, the toggling action occurs at the output or the next state of T flip-flop. This is a time evolving diagram showing the contrast ratio as a means to understand the power level difference between optical logic 0 and logic 1 state. And to conclude, all optical T flip-flop is realized with photonic crystal waveguide comprising of an array of chalcogenide rods in square lattice. And the proposed design is small, high contrast ratio of 28 decibel value and distinguishable range of toggling time about 0.8 picosecond. Therefore, it is potentially applicable for optical switching networks. Thank you.